On the night of February 23, 1987, at the Las Campanas Observatory in southern Chile, Ian Shelton photographed the large Magellanic Cloud. As he developed his plates, he saw a bright object that was not on the previous plates. He thought it was only a flaw, but he walked outside to check it. In the sky, he saw a star he had never seen before. An object appearing so suddenly, he knew must be a supernova. Ian Shelton telegraphed the news of his discovery to the International Astrophysical Union, the IAU. Using global computer networks, the IAU announced the discovery to the world.
Supernova is the most powerful event, the biggest cataclysm one can imagine in the universe. The sun will shine at this rate for about 10 billion years and put out 10 to the 51 ergs. The supernova liberates that much energy in neutrinos in 10 seconds times 100.
Designated SN 1987A, the supernova is located in the Tarantula Nebula in the large Magellanic Cloud, the galaxy nearest to ours. Even though the supernova is 170,000 light-years away, it is the closest supernova since Johannes Kepler saw one in 1604 in the Milky Way.
Supernovae that are visible to the naked eye are really rather rare. I think only 3 have, outside of the present one, have been seen in the last millennium. There was the Crab supernova, now known as the Crab Nebula, which was in 1054 and was even visible during the daylight.
SN 1987A reached a magnitude of 2.9, which is easily bright enough to be seen at night. It once was a faint star called Sandulic -69202, a blue supergiant, about 15 times the mass of our sun.
Well, one of the most important things that a supernova does do is to create new elements. It's a long-standing theory, and I believe this supernova and some other observations have confirmed it, that all of the heavier elements, things heavier than helium, have been produced as a byproduct of stellar evolution, with supernovae playing the dominant role. Now, how does this happen? Well, a star is always subject to its own gravity. So when it has no hydrogen to burn, gravity is going to win for a while, and the core of the star is going to contract and get hotter. And then it will ignite the next fuel that it has to burn, which is helium. It burns helium to carbon and oxygen, and it'll burn some of the carbon into neon and magnesium. And after that, it'll burn oxygen into silicon, eventually silicon into iron in the center of the star, about 1.5 solar masses. Now, it's a quirk of nuclear structure that when you've produced iron, you can't get any more energy out of nuclear fusion reactions. So the core becomes unstable at that point. Gravity is still there all the time trying to pull it down. And now with no fuel left to run on, the core collapses.
Small stars like our sun are not hot enough to burn carbon, and their nuclear fires die out. Then they cool over a period of billions of years to a very dark star, a black dwarf. Heavier stars are hot enough to burn carbon into oxygen, then silicon, and finally into iron. No more energy is available from fusion of iron nuclei, so the star stops producing heat. When the energy source is depleted, the gravity of the star causes the core to collapse inward.
And it falls very rapidly at speeds approaching a third the speed of light. And it collapses in a period no more than a second from something the size of the Earth to an object about 20 miles across.
In this giant nucleus, the protons and electrons of the iron are so close to each other that they combine to form neutrons. Thus, the core of the collapsing star becomes a giant ball of neutrons, a neutron star. If a collapsing star were big enough, its gravitational force would overcome even the forces that hold atomic nuclei together, and the core would become a black hole. Sandulic is probably not massive enough to form a black hole, so it reaches a point where its core cannot collapse any further. At this so-called point of maximum scrunch, the core bounces back and blows the rest of the star out into space, with an explosion energy over 10 times the lifetime output of our sun. This explosion is a supernova. The energy emitted by a supernova is primarily composed of neutrinos, particles that very rarely interact with matter. Neutrinos can be detected in huge tanks of purified water, buried in mines in Japan and the United States. 3 hours before the first optical observations of the supernova were made, these detectors noted neutrino emissions somewhere in the direction of the Large Magellanic Cloud. The neutrinos interacted with the purified water and caused flashes of light which registered on arrays of photodetectors in the tanks. These detections were not discovered until later, but they confirmed current theories about how a supernova explodes.
When a star goes supernova, it releases radiation over a broad spectrum at many different times. There's a very interesting portion of that radiation, which is the radioactive decay energy. When the explosion first takes place, the high heat at that time takes lighter elements, such as, say, silicon, and fuses them, burns them into heavier elements, such as nickel-56. That radioactive decays then into cobalt-56. And then the cobalt-56 then decays into something that's very common that we all know, that is iron. And in fact, it's thought that a substantial part of the iron that we actually see around us is produced in supernovae. So for a time, say, about 4 months after the supernova itself, all the optical light we see really has its origin in the radioactivity of the cobalt, but that radioactivity is not in the gamma ray region, but it's degraded into optical photons. We see it almost as heat, if you will. Later on, the remnant expands. The optical light curve starts falling off, and at the same time the gamma ray light curve starts picking up, and we start seeing then the radiation coming out as pure gamma rays. So when we're looking then at the gamma rays from the radioactive decay of cobalt, we're actually looking at sort of in real time at elements that have just been produced, say, less than a year before.
In the year following the supernova, several experiments measured 847 keV gamma rays as well as other gamma ray radiation. This included the solar maximum mission already in orbit around the Earth, which is run by NASA's Goddard Space Flight Center, and instrument-laden balloons, which were launched in Australia. Some gamma rays from the supernova are scattered, lose energy, and emerge as X-rays or ultraviolet radiation. Japan launched the Ginga satellite, which detected some of these scattered X-rays. NASA's rocket-borne experiments in Australia also observed radiation in this wavelength. Other rocket-borne missions and the International Ultraviolet Explorer observed in the ultraviolet spectrum. Ultraviolet investigations are used to detect atomic phenomena near the outside of the supernova envelope. Infrared observations explore the inside of the envelope and the dust layer of the star before it exploded. These measurements reveal information about the density and temperature of the supernova and the formation of molecules within the envelope and in nearby space. The Kuiper Airborne Observatory, operated by NASA's Ames Research Center, flew several experiments over New Zealand to observe in this region of the spectrum. Since infrared wavelengths are absorbed by the air, the experiments were conducted high in the atmosphere.
It's very valuable to continue watching the supernova. In fact, the supernova is going to be watched for years to come. We certainly expect to see enhancements perhaps in the radio region, expect to see perhaps enhancements in the X-ray region, and a real prize would be eventually to see the pulsar that presumably was born when the supernova took place. Right now that pulsar is buried deep inside, and all of us would love to see it eventually, and we don't know. It may be seen in the next year, it may be seen in 10 years from now.
Observations in all ranges of the spectrum were made. Scientists will gain valuable insight into natural nucleosynthesis, the formation of heavy elements. Our solar system was created from these elements. We will gain understanding of the history of the Earth, as well as the rest of the universe, by studying the deaths of stars.